Bismillah ar-Rahman ar-Rahim. So today we are doing paper 6, that is the alternative to practical from March 2023 for 0625 IGCSE Physics. There we are. So a student determines the diameter of a marble by two methods and calculates the density of the material from which the marble is made. Some marbles are shown full size in figure 1.1. Method 1. On figure 1.1, measure the length D. Oh, by the way, we began this, but there's something I want to share before. So, yeah, I had in my mind that, it's something we need to do before we start the paper, and then I just forgot. So, hey, let me put that on screen for you. Give me a sec. Okay, significant figures. Right, so significant figures are the digits in a measurement or calculated value that carry meaningful information regarding its precision and reliability, typically including all certain digits plus one estimated digit. Okay,
Really?
Huh?
Really?
Yes. Right, now just let's go through this. Let's take a look at what the physics syllabus has to say about significant figures, and then we can take sort of I'll explain that with an example, right? That has to do with measurement, like we're doing a measurement question. Okay, so I guess that's good that we took a look at that question first. So how do significant figures work? So if you just take a look at these 4 points, there's a bit of more detail, but as a general understanding, all non-zero digits are significant, right? So 1, 2, 3.45, whatever the number is, if it's a non-zero digit, even if there's a decimal, they're all significant. So 123.45 has 5 significant figures. By the way, this is all sourced from Britannica, right? I mean, there are others like Columbia Center for Teaching and whatnot, Montgomery College. So these are all proper sources, right? And I did read through the article on Britannica, right? If you want, we can go there. They explain the very same thing. We just scroll down. So yeah, all non-zero digits are significant. Right, so the value of 211.8, it's all non-zeros, that's 4 significant figures. Then all zeros that are found between two non-zero digits are significant. So 20,007, there are 3 zeros in between, but they're sandwiched by 2 non-zero digits. And so, right, they're all significant, and this gives us 5 significant figures.
Yeah.
Leading zeros, so all the zeros that come before a non-zero number, right, they are not significant. So something like 0.0085, how many significant figures does it have? It only has 2 significant figures, right? So, yeah. So something like, we write 001, right?
Yeah.
And so the number of significant figures for that is just 1, right? What are the other 2 zeros? They are called placeholders, right? Like, for example, writing 001, meaning that our counting can go into the hundreds, right? So we've mentioned the unit, which is 1, but we've kept the place for the tens and the hundreds, for example. Now, here's the thing, right? Trailing zeros for whole numbers that end with a decimal point. For example, someone's written 320 point, right? And just point. So this 0 at the end that has a decimal that follows, and just a decimal, nothing after the decimal, that is also considered significant, right? So in this case, there are 3 significant figures. Of course, if you don't write the decimal, you only write 320, then it will only be considered as 2 significant figures. So the double 0 at the the 0 at the end of 320, you're like, oh, 320. If you remove the 0, right, then it becomes 32. So obviously that matters. It does matter, but in terms of significant figures, it won't be counted, right? So 320 as a number only has 2 significant figures. The 0 at the end does not count.
Okay. Got that.
And then trailing zeros meaning the zeros that come at the end of a number to the right of a decimal place are significant. So, right, if it's written 12.000, right,
Yeah.
it is 5 significant figures.
Okay.
Yeah.
Yeah, okay.
Right. Also, there was another example. Let me just go back to that AI generation. So, yeah, so something like right 20.00, right, and also for example 0.500,
Yeah.
right, those are also significant, right, to my understanding. So just to review, obviously you can search this up. You got some images, some practice, I believe, over here. If you go into images, you can see someone shared this one. All right, so these are some examples of significant figures. So yeah, so for example, in chemistry we get like a concentration of 0.500 mole per decimeter cube, right? And so that is actually 3 significant figures. So the zeros coming before, if you look at number 10, right, in the image, the zeros coming before are not significant, but the zeros coming after are significant. So this number has 3 significant figures. All right, so you can take a look at this as well to have a better understanding of how this actually works. You can see numbers like 91,600 has 3 significant figures because the zeros that come after the 6 are not considered significant, right? And similarly, 10 centimeters has 1 significant figure, right? The 0 after the 1. So now taking those rules of significant figures, right, and then taking a look at the mark scheme, the syllabus, not the mark scheme, right, and just putting in a search. Yeah, so over here, can you see that?
Yeah.
So the syllabus says that the number of significant figures given for measured quantities, the number of significant figures given for measured quantities should be appropriate to the measuring instrument used. And the number of significant figures given for calculated quantity should be the same as the least number of significant figures in the raw data used in that specific calculation. Right, that's what the syllabus, says about what they expect, how they expect significant figures to be used. Now, does that make sense?
Yeah.
Okay. So now going back to our paper, and right, so we came across a bit of confusion with perhaps the rounding of values, right? The rounding
पता
of
है तुम्हारे पास तो
the
अब पूरा क्या खाएगा
rounding of values is also something, right, along with significant figures that needs to be looked at. Okay.
Okay. Yeah.
And so yeah, here, right, so what instrument are you going to use to measure this length? Obviously you're going to have the paper in front of you, and then you're going to like what are you going to use to measure the length D?
Mm, wait, let me think about this one.
What is going to be in your stationery box that you're going to use to measure the length?
The scale?
Yes, the scale or the ruler, right?
Yeah.
And right, you can measure right up to what is it, 0.1 centimeter, right, as the markings are given. And if the value is falling between two marks, right, each signifying 1 millimeter, if the value is somewhere between, you can kind of estimate up to 0.05 centimeter. So that's half a millimeter. Okay. So
Yeah.
when they say that the number of significant figures for measured value, so this is something you're going to measure using a ruler, right, should be appropriate to the instrument being used, right?
Yeah.
And so with certainty, right, the definition of significant figures, that with certainty you can measure up to 0.1, and then you can sort of estimate up till 0.05 centimeters, which is half a millimeter. And so you can give a value of up till, right, half a millimeter. So when you measure this, right, with a ruler, and obviously, right, you can't do that right now, I can't do that right now, and what you will end up with is 7.8 centimeter. Now this is, right, fine, because, right, normally we can measure up to 0.1 centimeter, right, with a scale, and so that is the number of significant figures we can give, right? And I'm assuming, because that's the answer, it's coming up to exactly 7.8. Right now students should not be getting varied answers over here, because it's a very fixed drawn line, so you just put your scale next to it and measure, right?
Yeah.
Now using your value of D, calculate the average diameter of one marble. Now how are you going to do that?
Find the, wait, divide it,
Divided by how much?
0.05.
Why will you divide by 0.05?
No, wait. Could you scroll up to the question? Wait. Um, by, wait, 1, 2, 5.
Yes, there are 5 marbles,
Yeah.
right? And so you will, so 7.8 divided by 5 is 1.56. Now here we apply the significant figures rule given the syllabus for calculated values. The calculated, right, it should be up to the least raw data, right? So number of marbles is maybe not the right raw data. 7.8, that's 2 significant figures, right? And we are getting 3 significant figures. So we're going to round this off to 1.6 centimeter, right? Because in the raw data for our calculations, 7.8 was the least significant figure used, right? I mean, two significant figures was the least used. Making sense how significant figures work?
Yeah.
Right. And so in all the papers you did earlier, probably because when I said that I'm a bit confused, for example, I think the answer we were getting for a particular question was 3060 and the mark scheme gave 3100.
Yeah.
Right, they rounded it up to 3100 instead of keeping it 3060. I don't remember which question and what the question was about, but I remember the value. And so if you go and look back at it, it's probable that the least number of significant figures given in the raw data for the calculation was 2 significant figures, right? And this is considered as 2 significant figures, and that's why because if you take this is 3 significant figures. Again, remember this 0 at the end is not considered, and similarly these 2 zeros at the end are not considered. So this is 3 significant figures, this is 2 significant figures, and so you're supposed to give your answer to a calculated value according to the least number of significant figures in your raw data for the calculation.
Okay, I think I'm getting a hold of it.
Okay, so when you're practicing further, keep that in mind when you are giving your answers. Okay, carrying on. Suggest why it is more accurate when using a ruler to measure D for 5 marbles rather than measuring the diameter for a single marble.
I think the ruler will get you the exact answer.
No, but they're asking why are we measuring the diameter of 5 marbles and then getting an average rather than just taking one marble and measuring that directly?
Mm, do not get any error.
So, right, you could say that measuring just one marble, the measurement will be uncertain, or measuring 5 marbles at a time will reduce uncertainty, right? Because obviously measuring a larger value in length is better than measuring small values, right? And that's because you're using a ruler, right? If you were using something like the micrometer screw gauge, for example, then perhaps, right, I mean, definitely you could very accurately measure the diameter of a single marble because it is that precise. But the ruler, the precision of the ruler is not enough to measure very small. I mean, you could, right? But taking something of you know, larger length and then getting an average out of it is a better technique. You'll probably be closer. So measuring 5 marbles reduces uncertainty. Or you could say, for example, that right, the diameters of individual marbles may vary. So if you measure one, the other marble may be slightly different, maybe like half or 1 millimeter off, right? So it might be 1.5, it might be 1.55, right? I mean, even this was 1.56, so it might be slightly different. And
Yeah.
so getting an average out of 5 is better. You only need 1 point because it's a 1 mark question. Okay. Method 2. Figure 1.2 shows 2 wooden blocks and one of the marbles. Okay, so you can see the figure over there. So you've got the wooden blocks over here, you've got the marble on a bench. Describe how the student uses the 2 blocks and the marble to determine a new accurate value for the diameter of a marble. Draw a diagram to show the arrangement, right? So they're asking you to draw it. You have to draw it. Describe clearly how the student ensures that the value of the diameter of a marble is as accurate as possible. So what are you going to do?
Show the arrangement of what?
Of how the kid is going to use the wooden blocks to measure the diameter of this marble.
He's gonna put in wait. He's gonna put the marble inside the wooden blocks to see how many fit.
Hmm?
That's what I'm thinking. Wait. Uh, honestly, I don't know this one.
No, I mean, like, what can the student possibly do using the 2 wooden blocks to measure the diameter of this marble?
He would put the marble inside the wooden blocks.
Between them,
Yeah.
right? So you've got this wooden block, and then you've got the marble, right? So when you draw the marble, it should be touching the bench, not suspended like what I just made, right? And then you've got the other wooden block, and because they're asking you to draw it, you have to draw it, and you'll make the other block, and you'll make sure that the blocks are touching the marble. There's no gap in between, right? And then you're going to measure this distance from edge to edge of the wooden blocks, right? So measure gap between wooden blocks, and okay, to add to this, how are you going to ensure, because they're asking, right, how is the student going to ensure that the value of the diameter is as accurate as possible?
Ensure it doesn't move.
No.
Like it's wait,
So what is the definition of diameter?
half of the
Diameter, not radius.
whole circle, right?
Passing through the center.
Yeah.
The distance between 2 points on a circle
Yes.
passing through the center.
Yeah.
Right. So something like that maybe. Right. And so it would be from any 2 points.
Yeah.
And so what you can do is you can possibly sort of measure the diameter from different sides of the marble. You're going to rotate the marble, right? You're going to rotate it and you're going to take like about 3 measurements at least. And then take a mean. Mean meaning average, obviously.
Yeah.
Okay, now figuring out the density. So the student uses the top pan balance in figure 1.3 to measure the mass of 5 marbles. He measures the mass M0 of a beaker without the marbles, and then measures the mass of M5 of the same beaker containing the marbles. So record the values of M0 and M5, right? And okay, so M0 is obviously 30.8 and M5 is 64.3, right? And so use these values to calculate the average mass of one marble. So first of all, what are we going to do?
Right. You need to find the average mass of one marble, right?
Yeah,
We gotta minus it, like
we're going to
30.
first find what the mass of the 5 marbles are. We're going to take the difference, right? So
Yes.
it's 64.3 minus 30.8, and that's going to give us the mass of the 5 marbles. And then we're going to divide it by 5 for the average. And so what is the result that we're getting out of this?
Wait. 6.7?
6.7, yes. Right? So 6.7 grams.
Yeah.
Okay, the student pours water into a measuring cylinder. He records the value V1 of the water level in the measuring cylinder. That's 26 centimeter cube. The student
Yeah.
then places 5 marbles into the water in the measuring cylinder as shown. Right, so these are 5 marbles. And remember, right, so what the concept behind this is that, right, when you place an object in water, the level will rise, right? Why? Because these guys are also occupying volume, and the measuring cylinder is there to measure volume, right? So,
Yeah.
so the water will be displaced and it's going to give you a higher reading, which will compensate for the volume that these marbles are taking up. So what is the reading over here? What is V2?
This one's hard. 40?
How is it 40?
Before it's sliding upwards, it is wait. Before the tilted line is 38.
Yeah, so 38. 38 is your answer.
Oh, okay.
You need to look at the lower meniscus. You don't look at this part. right? You don't look at the curved
You
part.
don't
You
have to look at the slanting part.
No, you look at the meniscus, which is the lower part. In this case, in case of water, in some cases, right, the meniscus is concave, right? It's curving upwards, and so you look at the upper meniscus, right? And this is again giving an example of chemistry for chemicals such as uh, potassium permanganate or potassium magnate 7, right? KMnO4. So they have an upper meniscus that you need to read, but for water, it's a lower meniscus, and you read the lower part, not the curving edges, right? And now that looks like a smiley face. Okay,
Yeah.
so the value is 38.
Okay.
So v2 minus v1 over 5. So we had 26 over there. So 38 minus 26 over 5. What are we getting?
This 30, 2.4.
Yes. All right. So this is for a single. This is like the average volume for one marble. Now, obvious.
This question was easy.
Yeah. Now getting the density, so mass over volume, so get the average mass, which is 6.7,
Okay.
and the average volume, which is 2.4. Right?
So 6.7 divided by 2.4.
Yeah. 6.7 grams over 2.4 centimeter cube. And so what is your answer?
2.791.
2.
What are you
2.791. That's four significant figures. What is the minimum significant figure in the raw data that we have used?
2?
2, exactly. So we round it off. So when we're looking at this, we want this to be 2. So we look at this value to round it off. This is 9. And so this will become 2.8
Okay. Yeah.
because 9
Yeah.
is greater than 5. So,
Yeah. We then added it.
all right. So is significant figures making sense now?
Yeah.
Okay. Describe one possible source of inaccuracy in the method described in C and suggest one improvement to reduce its effect. So the C method is, right, this measuring the average mass and then measuring the average volume and then finding the density, right? So what is one possible inaccuracy, and then based on that inaccuracy, how are you going to improve it?
Um, not reading the uh volume, like not reading the volume level at the eye level. Like
Parallax error?
yes.
Yeah, that's not going to fly.
No, wait, but wait. You have to read the measurement at eye level.
You do,
Yeah.
but yeah, but that's not an inaccuracy in the method, right? That's an
I
inaccuracy in your measurement. The method that they've used. So they're getting the
Oh.
average mass of the 5 marbles. They're taking the average volume of 5
Oh.
marbles, right? So what is an inaccuracy in the procedure, like technically the way they've done it?
Mm, I don't know, honestly. I thought the way I thought it was different, but the way you're saying it is different, so I did not think it that way.
Okay, so one way of doing this is maybe, right, you've used too few marbles. So, right, maybe, right, the uh, average mass or volume calculated is inaccurate, right? as number of marbles used is less, and so use a greater. Okay, don't use the hash in your paper, right? Write number of marbles for mass and volume estimates.
Okay.
Right. Another thing that's mentioned in the mark scheme is that the graduation of the measuring cylinder is too large, right? So maybe they use too large of a measuring cylinder, right? And so instead of using maybe 100 cm cube, maybe they could use a smaller 50 cm cube measuring cylinder, right? And with that, right, you put in the marbles, and so perhaps you're going to get better results, right?
Yeah.
All right, moving on. Question 2, a student investigates the cooling of hot water from different initial temperatures. She uses the apparatus shown. You've got a beaker, a thermometer, a clamp, you've got the boss, and the stand and the bench, right? And the thermometer is giving you a reading. The student measures the room temperature. Record the room temperature theta R shown on the thermometer. What is the room temperature?
21.
21.
Look how smart.
Yes, you know how to read.
Yay.
Describe one precaution that the student takes to ensure that this temperature reading is as accurate as possible.
Reading at eye level.
Yes.
This question has been repeated too many times.
Okay. Experiment A. The student pours a volume of 100 centimeter cube of hot water into the beaker and records the temperature theta A at time 0. She records the temperature of the water in the beaker every 30 seconds. Her readings for experiment A are shown in the table.
Okay.
Experiment B. The student repeats the process. She waits until the initial temperature theta B of the water is the same value as the temperature of theta A at 90 seconds. In
Okay.
experiment A. In the first time of table 2.1, record her initial temperature of theta B for experiment B.
Okay.
What
We
is, yeah,
we need to find the empty box.
yes, you need to fill in the blank. What is the initial temperature of theta B, right, at the start of experiment B? Read this,
84.
huh?
No, wait. Yeah, you want to say wait?
Yeah, read this again.
Okay. It's gonna. She said it's same value as the temperature at 90. So it's gonna be same.
This, she waits until the initial temperature, initial means when you're starting off,
Okay.
of the water in experiment B is the same value as the temperature in experiment A at 90 seconds.
So it's gonna be 90. No, wait.
No,
It's gonna be 92.0.
no, that's at 0 seconds. What is it at 90 seconds?
It's 85.0.
Yes, and so that will be the initial temperature of B.
Oh, okay. Okay.
Write a conclusion stating how the temperature at T0 affects the rate of cooling of the water. Justify your answer by reference to values from the result.
Mm, Let me think.
Okay, so right, we went from 92 to 80, which is a difference of 12 degrees centigrade,
Yeah.
right? Or 12.0 to be
I think
proper.
when the temperature increases, the cooling effect decreases.
Let's
Is
see.
that what I meant?
Let's see. What is the temperature difference between 85 and 75? That's 10 degrees centigrade
Okay.
over the same 180 seconds, right? That's 3 minutes.
Yeah.
So that means that what we can understand, when you're starting off with a higher temperature, the cooling is greater, right? Over the same period of time, you've lost 12 degrees as compared to when you are starting off 7 degrees less, right? So this is greater than 85, obviously, by 7 degrees.
Yeah.
You're starting 7 degrees higher and you're still, cooling off by 12 degrees centigrade over 180 seconds. Whereas when you're starting at 85, you're only cooling off by 10 degrees centigrade. And so, right, the higher the initial temperature or the starting temperature, the greater the rate of cooling,
So I was partially correct.
right? And so you also mention, right, experiment A shows cooling of 12 degrees centigrade over 180 seconds, and experiment B starting 7 degrees cooler, 7 degrees lower, cools only 10 degrees centigrade over 180 seconds. All right.
Yeah.
All right. Calculate the average cooling rate during the second half of experiment A. Second half. So that's after 90.
Yeah.
Right? Because 180 seconds, so half would be up till 90, and then the second half would be after that. To calculate the average cooling rate x1 during the second half of experiment A, right? Use the readings from the table and the equation given, right? Where t equals to 90 seconds. So they've given everything to you. T is 90 seconds, theta A 90 and theta A 80 are the temperatures at 90 and 180 seconds. Right? So at 90 seconds, you have 85 degrees. Yeah.
Yeah.
Minus 80 at 180
Yeah.
over 90 seconds. So what is the average cooling rate? Right? It's 5 over 90 basically.
Yeah.
So what are we getting?
Just a minute. 0.05.
0.0, it's recurring, right? 0.55555.
Yeah. Yeah. Yeah.
So it will be 0.056,
Yeah.
right? Because the uh, yeah, the raw data, right? I guess, I mean, technically this is 3 significant figures, and this is also 3 significant figures, and this is 1 significant figure, right? By that standard. And so the right now, keep in mind, right, what we have, like, so what we sort of know from what the examiner is expecting, that right, the minimum answer you're going to give is to 2 significant figures generally. Okay.
Okay.
Yeah. Okay, calculate the average cooling rate during the first half of experiment B. Right, so again the time is 90 and you're going to do 0 minus 90. So at 0 it's 85 and at 90 it's 79.5. So do that again. 85 minus 79.5 over 90. What are we getting?
Wait. It's basically a 5.5
Oh,
divided by 90.
by the way,
Yeah.
right, again, right, I need to remember what I suggest to you guys, right? Now they tend to do this, right? Sometimes they give you the units where you're supposed to
Sometimes
write the
not.
answer, sometimes not. And so make a habit of writing the units, even if they've mentioned it. It doesn't matter, right? If you just write like degrees centigrade, it's not going to take time, it's not going to cost you extra ink or effort, right? Why? Because now we just missed, this is degrees centigrade per second. It's a rate, right? If you don't write that, we're not going to get marks.
Okay. Okay. And this will be the answer of 0.061 degrees centigrade per second.
Calculate the average cooling rate. Okay, experiment 0.
0.061.
0.061.
Yes, and then it's recurring in the end. So degrees centigrade per second.
Yeah. Now, a student suggests that x1 and x2 should be the same. State whether your results support this suggestion. Justify your statement by reference to your results.
Are they the same? Wait. No, they're
So
not
for
the same.
experiment A, the cooling rate is actually 0.5056 and this is 0.061.
Yeah. Uh, I mean, they're not the same.
Hmm?
They're not the same.
Okay, now in all of this, right, despite what we said, what they're right, I believe that you could say that they're not the same, that they are right, but the question is that is it significantly greater, right? The difference between the two is 0.005, right? 0.061 minus 0.056 is right 0.005
Yeah.
degrees centigrade per second. Is that
Yeah.
significant? Is that really something that you would say, oh, the rates are really different?
The significant number are same, but the values are not same.
No, I'm not talking about significant figures. I'm talking about like, is this, it's like, right, 1,000 of a degree centigrade per second, right?
Yeah.
So does that really make a difference? Is that really something you're going to say, well, oh, that there's like a difference between the cooling rates?
Well, no.
Yeah, exactly. And so you would say that, right, the results support the suggestion. And the justification is that the cooling rates, right, and these are the average calculated, right, are within the limits of experimental accuracy. I mean, when you're calculating something, when you're measuring something in a performing experiment, you don't normally expect to get like the exact same values. Okay.
Yeah.
So you're going to have some cushion, right? The values can fluctuate, but are they different enough to say that, well, they're actually different, or are they, you know, okay? You say, okay, fine, they're the same, mostly. So they're within the range of experimental accuracy, right? With only a difference of 0.005 degrees centigrade per second between, right, x1 and x2. All right, state two variables which must be controlled so that the comparison of x1 and x2 is valid.
What does that mean?
Well, that means, right, they took a certain volume of water, right, and they heated it to a certain temperature, and then they followed the cooling. So what do you need to keep the same so that your measurements of temperature are proper? What other things that do you need to keep the same? Remember, in an experiment, you normally are testing only one variable, right?
The
So everything else is kept constant, or you use the
temperature?
word control. Yeah?
Temperature?
Which temperature? The temperature of the water is different in the experiment. So obviously that's not what you're talking about. Which temperature would you try and control?
The experiment one?
Yeah, but that's different, right? Experiment A has a starting temperature of 92. An
Oh,
experiment.
I want to keep the. Wait, no.
Yeah, go ahead.
I was thinking about time per second, but wait.
The timing is also the same. It's 180 seconds for both experiments.
Yeah. Or what else maybe? We gotta keep the water the same.
Yes, so that is actually one point, and they've mentioned that. So it's sort of like, right, just paying attention, right?
Actually,
Use the same volume of water, right? Because you're using different volumes of water, then obviously, right, it's going to affect the cooling.
okay.
Okay, what else?
Mm, the no, wait. Gotta keep the mass the same.
Mass of what?
The water.
I mean, if you're keeping the volume the same, then the mass is obviously the same.
Yeah. I don't know what else. Wait.
So there are two options, right? One is to maintain the room temperature.
I told you it was.
No, I asked you which temperature you're talking about, and you said the temperature of the experiment. What does that
Yeah.
mean?
Yeah. But I was on the right path.
Well, you thought of something to do with temperature, and so also use same type of beaker, right? So the material of the
But
beaker,
have in mind that you have to use some same type of what do you call the things that you're gonna use for the experiment.
yeah. Now, one thing to consider over here is because at the end we are saying that the cooling rate is the same, right? And so when we go back, and so this can happen in exam, right? All this explanation that I gave, that well, the experiment B is cooling faster and everything. The thing is that, right, this temperature difference isn't really something that to shout about. So maybe we can say that, right, maybe we can say that it doesn't really affect, or it could sit well, right, as long as we're able to justify it, because the mark scheme doesn't really say anything about this, right? So
Yeah.
I'm going to leave it as it is, but just to keep in mind that sometimes when you're answering this and you come to a conclusion, you come to the last answer, and you kind of get like a hint, like maybe what I did earlier is incorrect. Maybe I need to rethink that. Not necessarily. I'm not saying that you learn to, like, you start doubting everything you're doing, but it could happen, right? And if that is the case, then you go back, you look at it, and if you're not satisfied, what you do is, right, simply with your pen properly, right, just cancel this, right? You don't need to be like, don't do this, right? Very neatly just cancel that, and then mention, right, uh, answered on blank page.
Oh, so you're saying if you get the wrong answer, we're gonna rewrite in the blank page?
Yeah, so you can use the blank page and you number the blank page, right? So you blank page number 9, you mentioned that blank page number 9, and so this is,
Like if we think the answer is wrong.
yeah, so this is question 2C, right? And so I'm going to the blank page and I'm writing question 2C, right? Number it properly, and then you write whatever you think your answer is, and the examiner will take a look at it, they will grade it.
Okay. Yeah. Makes sense.
Okay.
Yeah.
Just go back on all of that. I'm just removing it from the writing.
Yeah.
Okay, but my explanation stays. Okay, we need to sort of hurry up and get through with this. Right, this is taking a bit longer than I was expecting. Okay,
How many more questions do we have?
we have only done half of it.
Okay.
Yeah, so questions 3 and 4. The question 3 is only the other stepwise thing, right? Question 4 is the planning one.
And that's the last question?
Yeah.
Okay.
So
Okay.
yeah, so let's try to sort of quicken our pace.
Yeah.
A student investigates the properties of a resistance wire. He uses the circuit shown. Didn't something quite similar come up in the
Yeah.
whatchamacallit?
Yesterday's paper.
No. The specimen.
No.
I believe the specimen ATP that we did was quite similar.
No.
Okay.
We're getting
So yeah. So the resistance, right? So he uses the circuit shown in figure 3.1. On figure 3.1, draw a voltmeter connected to measure the potential difference across the length of resistance wire.
You're getting deja vu.
Yes, I am getting deja vu. I'm saying similar. It's not the same, but it's the same approach.
Yeah. Okay. Let me see.
Yeah.
We're gonna draw the voltmeter near the crocodile clip. That clip is.
So the voltmeter needs to be in parallel.
Yeah. Actually, why do I think that this happened too?
Exactly. That's what I'm saying. Okay.
Yeah, this happened.
Yes, it did. Again, the values are different, but the approach is the same.
Yeah.
The thing that they're testing is the same.
Which is good, that's not gonna lie.
Okay, how about I skip this?
Okay.
Let's just do the planning.
Yeah.
The reason I'm skipping is because I feel that it's very similar to the one we did in
It's
the
repeated basically.
in the specimen paper. Obviously, the values are different, the calculation is different, the graph is going to be different, all of that, but the thing is the same.
Yeah. Okay.
Okay, a student investigates the motion of a ball through the air. Plan an experiment which will enable him to investigate how how the range of the ball depends on the angle at which it is launched.
Oh, these type of long questions is where I get mostly stuck at. It's gonna be hard. Oh yeah,
It's
definitely.
not hard, right? You need to understand which uh, concept is being tested, and you need to plan accordingly, right? And there's certain things that you always need to keep in mind, right? So let's read through this, and then right, they've actually given you, right, a checklist of things to mention.
Yeah.
So the range is the horizontal distance that the ball travels after leaving the end of the channel, right? So horizontal distance that it travels before hitting the ground. The apparatus available includes a flexible channel as shown, which can be bent to different angles. So they're showing that. A selection of balls, each of different diameter and mass, right? And so the purpose is to investigate how the range of the ball depends on the angle at which it is launched. Okay, in your plan, you should list any additional apparatus needed, right? Explain briefly how to do the experiment. You may add to figure 4.1 if it helps your explanation. State the variables to keep constant. Draw a table with column headings to show how to display the readings. Explain how to use the result to reach a conclusion. So they basically told you what to do.
You're not required to enter any readings in the table. What does that mean?
Just draw the table to show what kind of table you'll make.
Oh, okay. Let's do this.
Okay. So what's the table going to be like? It's going to be,
Obviously, rows and columns.
yeah, right? And so the heading, the first thing that you get is the independent variable. So what are you varying over here? You're varying the angle, right?
Mm-hmm.
And so the angle of launch,
So launch angle.
hmm?
So it's gonna be launch angle.
Angle of launch,
Same thing.
right? Uh, in degrees, so in degrees,
Mm-hmm.
and the range of ball in centimeters, right? And how many sort of repeats are you going to do? How many angles are you going to do?
Mm, 15.
Hmm?
I'm taking a random guess.
No, you're
15,
going to take 5,
10.
and for each, what you want to do is you want to take 3 repeats.
But why don't you do this? Make 2 more columns for ranges.
Why?
Like range 1, range 2, range 3, instead of compiling all the repeated one in the same column or the row, you can say.
Yeah, you could do that as well, right? So you could get angle of launch.
No, no need to draw the angle of launch. Just like
Yeah,
draw,
yeah.
draw.
And then range of ball in centimeters, and you could do, right, experiment 1, experiment 2,
Exactly.
experiment 3. Yeah,
Yeah.
and you could do that. So if you feel that the table is cleaner that way, and then you do 1, 2, 3, 4, 5, and so you make that 1, 2, 3, 4, and 5. Yeah, and so that's what the table will look like, right?
Yeah.
It could also be like this. It could be like that. That works as well. Okay, so you get the table, and the table is worth 1 mark.
Okay.
Okay, so you get 1 out of the 7. Now, what are the apparatus that you need? Let's write over here, right? So you obviously need a meter rule to measure the distance,
A scale.
not a scale, meter rule.
Okay.
because a scale is like either 15 or 30 centimeters, right? In the lab, what you're going to get is a meter rule. So it starts from 0 all the way till 100 centimeters. And right, how will you adjust the angle? How will you know what angle this is? So what are you going to use to measure the angle?
The angle scale, that semicircle thing. I don't
Yeah,
know what's
what
that.
is it called?
Angle scale?
No, protractor.
Yeah.
Protractor. You mentioned that. Explain briefly how to do the experiment, right? So obviously you set an angle, launch ball, measure range, right?
Oh, we want to write just these 3 points?
Well, that is how the experiment is going to be done,
Oh, okay. So,
right?
no, what I'm saying is,
After this, right, you're going to do two things. Take measurements for 5 angle values and repeat thrice for each angle. So you're going to mention that. Okay. What are you going to keep constant? You're going to keep, for example, the mass of the ball constant, or you're going to keep the diameter of the ball constant, right? Because you're mentioning that you have balls of different diameter and mass. So every time you want to use the same ball, right?
yeah.
Use same ball, right? So for example, you're keeping the mass constant. Another thing you can keep constant is the height of this thing from the floor. Okay, because that will sort of affect how quickly it reaches. Like if it's higher up, then it's also going to travel some distance while it's falling. If it's very close to the floor, it's going to hit the floor immediately. So that's going to affect, right? So you want to keep it at the same height every time. Okay, how are you going to you know get, what are they mentioning? How are you going to use the results to reach a conclusion? So first of all, because you're repeating each one thrice, you're going to take a mean, right? Ball range for each angle, right?
Yeah.
And you're going to compare if launch angle affects ball range. You can possibly plot a graph, right,
Okay. Yeah.
of launch angle. So the independent variable, the stuff that you're changing, is always on the x-axis, right, versus ball range, right? So launch angle per degree and ball range per centimeter on the y-axis. And that's right. So all this scribbling over here, you're going to write it as bullet points over here in the space provided. If you need, you can go to the blank page, and we're done. Did that
Okay.
make sense? So in principle, right? So the best thing is that they're telling you what to do. Right? Now, some things to always keep in mind, right? You need to, like, because they're telling you, right, mention the apparatus, mention how to do the experiment, and they're not mentioning this, but always mention how many different sort of settings you're going to use. So like we said, like, do 5. Whatever you're doing, do it 5 times. And for each setting, repeat it 3 times. They're not going to mention this in your instructions, but that's what you need to do. Always remember that.
Okay.
Always mention what you're going to keep constant, right? Just, even if they're not asking you, draw a table if you think that, and always mention how you are going to use the results to come to a conclusion. So this is the process for any planning that you're given.
Yeah.
Okay, it doesn't matter what kind of experiment. The last time we did it was like dropping a ball and finding the size of the crater it makes from different heights, right? Or I think it was different masses of the ball or whatever, right? So, right, even there, like use 5 different masses, keep the height same in that case, keep right, and repeat each, like the drop for each ball 3 times, and also so the approach is the same every time. Obviously the situation is different, so you mold your experiment according to the situation that's required. Okay,
Yes.
any questions?
No.
Then today was our last class, right? I hope all of this helped you. Do continue with your prep, right? I'm still available if you need any guidance, and right, so you can reach out and I'll try to help as best I can. And I wish you all the best, right? It was a pleasure,
Yes.
right?
Well.
And right, go ace it. I mean, right, whenever your session is, right? Hopefully in November,
Yeah.
right?
Yeah.
All the best, and I'll see you around.
Okay then. Inshallah. Allah Hafiz.
Allah, Allah Hafiz.